Okay, so we do that, and then what we want to do now is actually implement this solution using our matrix decomposition technique in MATLAB down here. All right, so we're going to go to MATLAB now. Got a lot going on in this lecture with files and stuff. Okay, so this program here is the implementation of this problem in MATLAB. All right, so we start off again by clearing memory, clear all, and then entering all the data in. Unlike ease, MATLAB doesn't handle units, so you have to do all that stuff yourself. So you might even, as you're entering in information, double check the units in ease and make sure you get the conversions right before you enter it into MATLAB. Just take that extra step. Okay, but so we have all the geometry, the temperatures, current, all that, and then our cross-sectional area. So again, here's where the actual model is being implemented. Okay, so we discretize our domain into n nodes, and we do that using the for loop. Right? And in MATLAB, the for loop is really similar to the duplicate loop in ease. But unlike duplicate, it's not actually duplicating each equation. It's just performing the procedure however many times you say, substituting out I as needed as it iterates through it. And so okay, here we have the x position of each node, and then you indicate the index using instead of square brackets, it's round brackets, right? So xi is equal to, this is the same thing we had in our ease program, right? So this establishes our nodal positions. Okay, here's the length of each node. And then what you have to do is you have to tell MATLAB how big your matrix is going to be. We're trying to get to this A matrix, an X vector, and a B vector. So before, you can't just go in and start putting stuff into a variable space without telling it first what the size of this thing needs to be. So you do that first with, there's kind of two ways of doing it. Zeros will do it. It's the most obvious way. So if you say A is equal to zeros nn, what you're saying is, I'm creating a matrix that's n rows and n columns. And then I'm going to initialize that with a bunch of zeros. Okay, so now you, in memory, have this big 2D array of zeros. And then you can go through and assign values based on your actual computation for each equation. That's, like I said, one way to do it. It turns out that having a really big matrix that's mostly zeros is actually not that computationally efficient. And it's mostly zeros here because for every single equation, then every node only interacts with an adjacent one or two nodes. Right? So for every n equation, all the n equations, every position only considers basically maximum three variables. So really you have this very sparse matrix. And if you're trying to solve or invert a matrix that's got a bunch of zeros in it, it's going to take a lot longer than if you just deal with the sparse matrix to begin with. Okay, so the other way of assigning this A matrix is to call this sparse allocation function, or SP-alloc, spalloc, whatever you want to call it. Right, and the idea there is you say, okay, here's my overall dimension, n by n, but then here's how many values I actually expect to have, which is 3 times n at the most. So in memory, it's going to go in and actually allocate 3 times n spaces and associate with those with the indices that you're trying to assign. So we'll do it that way, and it speeds things up a little bit. Oops, like this. Okay, so we're going to allocate that much. What happens if you go over it substantially is probably just a memory penalty, not like it's going to fail. But it's a good way to speed up the program. Okay, so we tell it A is this, we tell it B is an n by 1 vector. Right, so n entries in one column. And then our job is to assign the A values. Okay, so here we say A11, if we look back at our solution here, right, A11 is going to have to be this stuff, right? What's multiplying, let's get out of there. What's multiplying T1? Okay, if we look here, it should exactly be the same. This is what we just did to solve for that T1 coefficient. Okay, A12, it was that shorter term that's here, and then B1. So we're doing this first for our boundary condition, node 1. Right? And this looks a little different from node I and node N. So we have to do it separately. So first we do node 1. And then we do the same thing for all the internal nodes. Again, we're just trying to fill in this A matrix so we can solve it. Right? A, now II, so this would be like the equation for TI, or the term for TI. And then I minus 1 would be the term for T, I minus 1, I plus 1 would be TI plus 1. And then here's your B, right? So we do that then for all nodes internal, which are 2 to n minus 1. Okay, and then the last thing is node n, which is really similar to node 1. But again, it's a different equation, so we have to handle it differently. Okay, so you should have kind of 3 groupings of these assignments, 1 on each boundary, and then 1 for all nodes I. Okay, last thing is, how do we actually solve this equation? So if you look back here, right? So how do we actually solve an equation like that's like this? Let's say our equation is A. Oops. Come on. Okay, our equation is A times X equals B. So how do you actually solve this equation? You can't just divide the equation by A, right? Matrices don't work like that. There's no such thing as dividing by a matrix. So what we have to do is multiply both sides by the inverse. Right? So we would multiply this side by the inverse and multiply this side by the inverse. The inverse of a matrix times itself gives the identity matrix, which is just a diagonal of 1s. Okay, so a diagonal of 1s times X just returns X again. But we have to figure out, we have to find this inverse of this matrix. So actually, this we know is going to become identity. Identity times X is just X. So this is just saying X is equal to B times inverse of A. So we still have to find the inverse, but if we find the inverse multiplied by B, that gives us our temperatures in that X vector. Okay, so looking back at MATLAB, how do we do that? Well, there is a function called inverse, right? Here, T equals the inverse of A times B. So we could take the inverse. It sort of separately solves for the inverse of A. So MATLAB will actually go off separately and find the inverse of A, come back, and then multiply B by that inverse that you just found. But again, that's actually not the fastest way to do it. In MATLAB, the fastest way to do it is to consider that A backslash B as one kind of unit, and you use this backslash notation, I guess, to solve the problem directly that way. Okay, so this is a little speed trick. You can do it either way, but the A backslash B is actually much faster. So we'll do it that way. So now our temperatures are going to be A backslash B, that's the inverse of A times B, and we can just run this now, all right? I'll pause. Any questions on all this stuff so far? Okay. Okay. Okay, we can run this now. What do we do? We said there's how many nodes? 101 nodes. That should be solvable in ease. Yeah.
With the spatial like spell, if you get the 3 times n and it's actually 4 times n for one of the, is that okay? Will it
I think it's okay. Yeah. Usually what you want to do is you set like an upper bound. If you're familiar with programming in any other language, if you allocate a certain amount of space for something in memory before it runs a program or as it's starting, it'll actually in memory create kind of a region for this stuff. If you go over that amount, what it has to do is it has to destroy that, physically move everything to another place in memory, right? So let's say you had 10,000 things and then you got to 10,001. Now it's going to take that array and destroy it, move it somewhere else, and allocate 10,001 spaces. Now you go to 10,002, it might have to do that exact same thing again. Right? So every time you violate that constraint, it's like a computational penalty. But I don't think it's going to crash. But usually you want to just be a little conservative and overestimating. You can't have more than 3n for this because there's no physical way a node can interact with nodes 2 out from it. Right? Okay, so we solve this, we can solve this equation for our setup, see if it runs. Okay, if I can get it down here. Okay, so here's our plot, right? This looks familiar, hopefully. This is what we did with ease last time. Now we've got 101 nodes and we're evaluating the temperature. Yeah, there's a peak kind of in the middle. That's what we saw before. That's our solution. One thing to know is it solved really fast, right? It almost in a blink it solved. And in fact, if we go back and make this, I don't know, something bigger, let's say 10,001 nodes. You know right away, there's absolutely no way that ease would solve this, right? Ease is limited to 12,000 variables total. And here we've got 10,000 associated with each T, so that's at least 30,000 plus some others here. So if we run this, again, like amazingly fast, it solved it. So it's just, let's see here if we can get this. Yeah, and it's so dense you can't even see the nodes, but it solves it really quickly. All it's doing is inverting this big sparse matrix, getting it back, multiplying it through by your B coefficient, and there's your answer, right? So it's a pretty convenient way of doing it. If you can find a way to get all the coefficients into that kind of linearized form. Yeah, question?
So in the last section, you mentioned that essentially problems that have some meaning happen in specific regions, you want to allocate more nodes at near that region. Is there a unique function that does that in MATLAB, or is it something that you have to do?
There are, we'll get into it when we talk about non-steady state problems. So in those problems in particular, you usually have a lot of things going on right when the boundary condition changes in time. And so we'll talk about it. They're called like Ode functions. And one example would be Ode 45. It's a specific function in MATLAB. You call it, you give it the function, and it will automatically detect the right time step to move forward. So if the derivatives and things aren't changing a lot, it elongates the time step. But that same kind of thing can be applied for a numerical spatial solution like this.